Hi everyone, welcome to the next session for design and drawing of reinforced concrete structure. Last class we have seen about the analysis of flanged beams when flange is uniformly stressed. In today's class we are going to discussing about the same condition, that means when the neutral axis is lies within the web portion but the flange is not uniformly stressed. In those situation, how we should have to analyze the and how we should have to design the analysis of flanged beam and the design of flanged beam, that we will discuss in today's class. In today's class is only one thing is different. The remaining same procedure we are adapting from the case number 2a. What you are discussed in the case number 2a, that same thing we are repeating here. The only thing is changing only the lever arm distance, that is only the lever arm it will change. How the lever arm is changing due to changing of this lever arm, how the complete analysis and design procedure it will may vary, we will see in this lecture. And if you see here, this is a regular T-beam, that is nothing but a flanged beam, and here where BF is the width of the flange and DF is the depth of the flange, and where NA is the neutral axis. Neutral axis, it is the axis which divides the total compressive force and the total tensile force. If you observe in this diagram, in this direction we will have the total compressive force, as well as in this way we are have the total tensile force T, and here we are provide the bottom area of the steel to resist the tension, and where here BW is the width of the web, and from this bottom of the flange portion up to the surface of the bottom of the concrete we are having the depth of the web. The depth of the web we are naming it as DW, and this is the stress block parameter. Again, if you see here, for this flanged beam, when neutral axis is lies in the web portion and the flange portion is not uniformly stressed. Not uniformly stressed means, if you see here, while learning the assumptions for limit state of collapse under flexible condition, we have seen that the stress block is parabolic from neutral axis to the strain of 0.002 and rectangular up to the strain of 0.0035. In previous condition we have discussed about, suppose if you take this flange portion, in this flange portion only the rectangular stresses are developing in the previous condition. There is no parabolic stresses, that means linear portionally varying stresses are not getting in the first condition when depth of neutral axis exceeds the depth of the flange. If you see here, in present condition the stress is not uniformly distributed. That means in this flange portion some amount of rectangular portion stresses are developing, as well as some amount of parabolic portions are developing on the beam. Some amount of rectangular portion of the stresses are acting, as well as some amount of parabolic portion of the stress also acting. If you see here, for this flanged beam, the stresses developing for this particular beam, that is not uniformly stressed. In previous condition, this entire stress block, that means this entire flange block having the stresses. If you see here, the present condition we are having stresses up to some certain distance. That distance we are naming it as YF, where YF it is the distance from the top of the compression fiber to certain distance it getting the stresses on this particular T-beam. For this type of situation we have to calculate the total compressive force, total tensile force, moment of resistance in compression, moment of resistance in tension. If you see here, this is our regular stress block, and here this is the total compressive force 3/7 of XU. If you see in present condition itself, it explaining about 3/7 of XU is less than the depth of the flange. This is your total depth of the flange, and this 3/7 of XU is less than this depth of the flange. If you observe in present condition, in previous condition, the stress block is 3 by 7 of XU is greater than the DF, where depth of flange is here, the stress block may exceeds in the rectangular flange. That is the previous condition we have discussed. If you see in present condition, the stress block what is available here, this stress block is stressed with the rectangular portion as well as parabolic portion for this particular type of flange beam. For this analysis, again we are considering the limiting moment of the beam, as well as to carry the additional moment we are providing the additional bars to reach the additional moment of the beam. Again, if you see here, again we are considering this also same as previous condition of our simply rectangular beam, that is nothing but our singly reinforced rectangular beam. This is the web portion, this is the web portion. The same web portion we have drawn here. The drawn figure we are naming it as figure 1. For this figure 1, we should have to calculate the how much amount of total compressive force acting on the beam, as well as how much amount of total tensile force acting on the beam, that we have to calculate. Again, we know that total compressive force equal to 0.36 into FCK into BW into XU. Total tensile force also we know, that is where here C1 and this is a T1. C1 equal to 0.36 into FCK into BW into XU. T1 equal to 0.87 into Fy into AST2. The distance between the lever arm we are having D minus 0.42 into XU. This is all thing what you are written in our case number 2A. The same thing will be repeating here. You need not to change anything. Okay. Next, come to this. If suppose this is figure 1, and come to this figure number 2. For this figure number 2 also, we know we have calculated this web portion. Now we have to calculate the how much amount of compressive force acting for this flange beam, and what is the moment capacity of this flange beam. The total width of the flange we know that it has BF. We should have to calculate this flange width, and we have to calculate this flange width. That is nothing but BF minus BW divided by 2. This half, again this half width also we have to calculate. That means BF minus BW divided by 2. This is the total flange width BF, and this BF minus BW, this is the half. BF minus BW divided by 2 half. This half and this half, we will get the total BF minus BW. For this, how much amount of total compressive force acting on the beam, as well as how much amount of tensile force is acting on the beam, that we have to calculate. Again, if you see here where this YF is the centroidal distance, that is not uniformly stressed, that YF value we are calculating by using one formula. That calculation of YF is nothing but YF equal to 0.15 into XU plus 0.67 into DF. 0.67 into DF. This is the only new thing coming into our present discussion. For this YF, if we are calculating 0.15 into XU plus 0.61 into DF. In previous condition, what you are discussed, where you are having the DF, in that case, if you substitute your YF, the condition is finished. The entire design is over, finished. Okay, again I am repeating here, where YF equal to 0.15 into XU plus 0.67 into DF, where XU is the depth of the neutral axis that divides the total compressive force and total tensile force. By using that, we can calculate the actual depth of the neutral axis, and DF is the depth of the flange. By substituting all these parameters, we will get the YF. YF is the condition when the flange portion is not uniformly stressed. In those situations, we will calculate the YF. Except this, what you are discussed in our previous condition, the same thing will repeat for this procedure also, where you are having the DF in the previous condition. In that situation, instead of DF, you should have to substitute the value of YF. By substituting this value of YF, we will analyze the same design procedure. Directly I will write the again total compressive force and total tensile force, moment of resistance for the compression 1, moment of resistance for the tension 2, total compression for figure 1, figure 2 equal to moment of resistance for the total compression, total tension in figure 1, figure 2 equal to total moment of resistance for the tension 2. That we will write here now. Okay, now I have written the all total compressive force for figure 1, total tangential force for figure 2, as well as lever arm distance, as well as total compressive force for the flange portion, total tangential force for the flange portion, as well as lever arm 2 for the flange portion of the moment of resistance of the capacity of the section. That is moment of resistance for the figure 1, moment of resistance for the figure 2. Next, moment of resistance in tension zone for figure 1, as well as moment of resistance for the figure number 2. If you see here from figure number 1, this is our regular rectangular beam. For this regular rectangular beam, we are having the total compressive force. The total compressive force C1 equal to 0.36 into FCK into BW into XU. Neutral axis lies within the web portion, hence why we are taking the width of the web as a BW. Next, total tangential force T1 equal to 0.87 into Fy into AST1. This is the area of the steel bars we are providing here. That is for limiting moment capacity of this section, AST1 equal to, that is the number of bars. And again we are having the lever arm distance. That lever arm distance equal to LA1 equal to D minus 0.42 into XU. That is nothing but the distance between the total compressive force and again as well as the distance between the total tangential force. That lever arm distance we are having minus D minus 0.42 into XU. Already we have calculated. Again if you see here in figure number 2, this is the figure and this is the flange portion. From this flange portion, we have drawn here one imaginary line. That means here we are not providing any concrete. Already we have, this is the concrete portion. Just we are providing some additional steel reinforcement to resist the additional moment. And again, if you see here, this is the width of the web. And from this width of the web, we know the total width of the flange BF. We have already calculated for particularly this width of the web. Hence, we are calculating the remaining portion of the flange. That remaining portion of the flange is nothing but BF minus this half portion, that is nothing but BF minus BW, BF minus BW. If you see in our present condition, in previous condition, we have considered the total depth of the flange. But present condition, when stress block is not, when the flange is not uniformly stressed, for that particular condition, we have taken this value as YF. We are taking this value as YF. For this particular YF value, we should have to calculate the total compressive force and total tangential forces. Okay, you should have to multiply YF instead of DF for the previous condition. If you see here, again we are having the total compressive force equal to 0.446 into FCK into BF minus BW. In previous condition, we have considered the entire flange. That means uniformly stressed. But it is now the present condition, the block is not uniformly stressed. Hence why we have to substitute here the width of the flange as YF. Width of the flange as YF. In previous condition where you are having the TF, in that place just substitute the YF, your second condition will finish. That again T2 equal to, we are having the 0.87 into Fy into AST2. Lever arm 2, again we are having total effective depth. Suppose from this top of the compression fiber to the total central distance of the bar, we are having this as a D, and this is the portion the total compressive force acting, and YF by 2 the central distance of compressive force acting on the beam. For this the resultant will be D minus YF divided by 2. In previous condition our block is uniformly stressed, hence why we are taking D minus DF by 2. In present condition the flange portion is not uniformly stressed, hence why we are taking the YF value, that means D minus YF divided by 2. Okay, from this we have calculated the lever arm distance. Next final step is we have to calculate the moment of resistance for the compression as well as moment of resistance for the tension. That is nothing but moment of resistance equal to moment of resistance for figure 1, moment of resistance for the figure 2, as well as if you consider the flange, if you consider the tension force also, tension force we are having T2 into L2, again T2 into L2, where T2 is the total tangential force, for figure 2, sorry, T1 into L1, T2 into L2. Total tangential force for this diagram, total tangential force for the figure number 2. Again total tangential force for both condition. If you see here, moment of resistance of compression equal to compressive force C1 into lever arm A1. Next, compressive force C2 into lever arm A2. This is the condition what you were discussed in the first condition. That is nothing but 0.36 into FCK into BW into XU. This is the stress, and D minus 0.42 XU. This is the lever arm distance for the figure number 1. Again from figure number 2 we are having 0.446 into FCK. This is the stress of the concrete, BF minus BW. This is the width of the flange. Next we are having the lever arm distance. That lever arm distance is nothing but D minus YF by 2. Again you have to remember here, D minus YF by 2. In previous condition, uniformly stressed, DF directly you are taking. Now our condition is different, and so you are taking lever arm as D minus YF by 2. Next, as well as moment of resistance for tension equal to 0.87 into Fi into AST1, D minus 0.42 into XU plus 0.87 into Fi into AST2, D minus YF by 2, where YF is the value we are getting from YF equal to 0.15 into XU plus 0.67 into DF. This is the value for the YF when the stress block is not uniformly stressed. How much depth the stress block is not uniformly stressed, that from this condition we will calculate the not uniformly stressed block depth. Up to now this is the entire analysis calculation for the analysis of flanged beams when neutral axis is lies within the web portion, as well as the stress block is uniformly not stressed, and 3/7 of XU is the 3/7 of XU is less than DF. This is the condition we have to apply. While analyzing the problems, we have to check the given problem for what type of analysis it will be liable. That means when XU is less than DF, that is condition is different. When DF is greater than 3/7 of XU, that condition is different. When 3/7 of XU is greater than the DF, that condition is different. Based on our assumption, which condition is suitable, based on that particular assumption, based on that particular calculation, evaluation, we should have to analyze and design this flanged beam. Up to now, this is the complete analysis procedure of flanged beams. In next class, we will solve some problems for this particular analysis, and after we will solve the design of L beam and design of T beam. Thank you.